Hello everyone. Let's keep talking about a few concepts in calculus-based physics, electricity and magnetism. Let's talk about Gauss's law a bit with some of the problems that are present. All of these problems will scroll at the end of this video. I may break up the discussion of chapter 25, the problems, from pages 781 to 786, from pages 781 to 786 in the Katz book, first edition. I may break up the discussion into two films. We'll see. We'll see how things proceed. But essentially, if there are two films, this will all scroll. All these answers will scroll at the end of each of the two films. If we go two films, if we make one big film, we'll see. If we make one big film, then it'll just be all this. We'll have to scroll just once because it'll be one film. So all of these problems will scroll. You will see them clearly. You'll know their solutions, and it'll be as simple as that. At the very least, I will try, when discussing chapter 25 from the Katz book and some of the problems, as we said, every single one of these problems you will see, scrolling at the end of the video and or videos. But for sure, I'll try to do problems 16, 17, 29, 30, 33, 34, 43, 57, 64, 67, and 78. There is possibly another problem that I'm going to bring into the whole matter, leaving, we're at least going to do 11 problems over the course of one or two videos, as we said. We'll see how the whole thing proceeds. But this is, this is where I'd like to go. The 11 problems at least I'd like to do. There may be another one I'm going to bring in related to this chapter that we might, if the circumstances permit us to do so, then we'll go that way. But we have this right here, guys, and like I said, for now we'll leave it up here. Eventually we'll erase it, and we'll proceed from there how we're doing this stuff. So this is some of the practice physics that we're doing, obviously. So, okay, guys, let's talk. For problem number 16, a circular loop with radius small r is rotating with constant angular velocity, omega, in a uniform electric field with magnitude E. The axis of rotation is perpendicular to the electric field direction. The axis of rotation is perpendicular to the electric field direction and is along the diameter of the loop. Initially, the electric flux through the loop is at its maximum value. Write an equation for the electric flux through the loop as a function of time in terms of small r, E for electric field, and omega. And problem number 17, closely related to it, they're saying it's exactly the same question essentially, but it's not at least the exact same setup, but the initial conditions are different from problem number 17. All right, we'll cross every bridge, and that bridge, in fact, when we're ready to cross it. But right now, let's take a look at number 16 and how that actually proceeded, how we actually got that. So what you're saying is, how are you going to write it? Well, I guess it's easy. You hear me say this a lot, you guys. Some things are just easier done than said. The flux, which is capital phi sub E, the flux electric, and there's a B field flux too, right? That will, that gets talked about at one point or another, right? But right now we're talking about the electric flux. The flux, capital phi sub E, is equal to the amount of E field that is hitting an area, and the cosine phi, where phi is the angle between the E field and the A vector. The A vector points perpendicular to the area. So if you had, let's say this is a side view of an area, and the area was A, they associate it with the vector A vector. And if the electric field comes straight out and there's no angle between this, zero angle between the two, then the cosine of 0 is 1, and it's just the magnitude of A times the magnitude of E. Magnitude of A vector times the magnitude of E vector. If for some reason, I mean, there's more to this. I mean, potentially more to this, but let's keep it pretty basic. If you're looking at a side view of an area, and again, we said we had the area vector coming out like this, and the E field was coming like out this way, and this was phi, there's where you're getting the cosine of phi, okay? So, as you know, so there's a lot to be said here. So that's kind of one view here of what's happening. Now, if this thing is, this cross-sectional area is right here, and this is the A vector, straight on when it's right here, and this is E vector coming out here, that's great, but when it turns a little bit, let's say you were to, you know, let's turn a lot. Let's turn this thing at a 90 degree, and it's rotating like this, not like that, but into the board and then out of the board. If you had it at the perpendicular, the A vector comes out, and the E vector is doing this. That's a 90 degree angle. This guy's coming out. You know, the A vector is coming out. The E vector is going this way. Cosine of phi is the cosine of 90 degrees. E times A times the cosine of 90 degrees is going to be 0. So this is going to be rotating, and we're going to keep getting different answers. We're going to hit a whole myriad. Phi is going to go anywhere from 0 all the way around 360 degrees back to 0, or all the way around 2 pi radians back to 0 radians. It's going to be multiples, obviously. You know, 2 pi radians is identical to 0 radians. If you double 2 pi radians, 4 pi radians is the same as 0 radians. Just like 360 degrees gets you back to 0, if you double 360, that's 720, that gets you back to 0. If you triple 360, 1080, that's back to 0. If you go 4 times 360, 1440 degrees, that gets you back to 0. So this is it's a cyclical situation going on here, and that's essentially some of the argument of what's happening here. So what's going on is they're saying they're starting this thing in a particular way, and just be very careful how we're doing it, I guess. Phi is omega times t. Well, if t is equal to 0, remember this thing started with the E field hitting flush straight on the whole area, broadside. So the area vector and the E vector were collinear and 0 degree angle between them. So at t equals 0, you're going to get phi equals 0. I don't need to do an addition of something else on here, to a phase angle, so to speak, to kind of get an idea what's happening. Leave it like that, you're fine. So what happens is, essentially, EA cosine phi, that's cosine omega t. Absolutely it is. Now, we're not done, but this is telling us a whole lot, is what it's telling us. You're one step away from being done, basically, guys, to really make this thing into a somewhat rigorous presentation of what we're trying to say and explain what they're asking us. We know, we've said that. EA cosine omega t. Well, what is A? Well, didn't they tell us it was a ring? A ring with radius r. Well, what's the area? What's the area of that ring going, things going through it? E pi r squared cosine omega t. And that's all they're trying to say there. And that's 16. They're playing this a bunch of ways here, guys. So for 17, they're about to play the same game. Now here, again, initially this whole thing started with the cross-sectional, the sideways view and the E field going right through it. Well, the E field goes right through it, and the sideways view had an E vector that was parallel to the E field. It was a sideways view, and the sideways view had the E field going straight through the middle, so to speak, of that area. And the area itself had an area vector that was parallel to the E vector. So E vector and A vector were collinear. The angle between them was 0. Okay. For 17, a circular loop with radius r is rotating with constant angular velocity omega in a uniform electric field with magnitude E. The axis of rotation is perpendicular to the electric field direction and is along the diameter of the loop. Everything that they told us in the past is being said verbatim here, once again, for problem 17. Initially, the electric flux through the loop is 0. Write an equation for the electric flux through the loop as a function of time in terms of r, e, and omega. With the other one, with the one that we just did here for problem 16, initially the electric flux through the loop is at its maximum value. Its maximum value was E vector dot A vector was E times A times the cosine of 0, which was E times A. So you started out that way. At time t equals 0, the initial value was these guys lined up in such a way that E vector and A vector were collinear. That's the way they lined up. Here, for 17, it's about the exact same problem, but they're saying the lineup's different. You know, at time t equals 0, this thing lined up at a maximum. Okay, does that work? Yeah, at t equals 0 here, 0 times this is 0, cosine of 0, radians or degrees. Radians are usually the safest way to go. It's the most natural degree measure based on the number system in general, based on the real number system, and based on other number systems also, I guess you could say, and some other number systems. You can have the complex numbers. The real most natural way to look at angles is with radians. It lines up, it's got the same measuring stick. The radian has the same measuring stick associated with it as the real number line. And then from the real number line, you can construct other number systems, the imaginary numbers and generally the complex numbers as they talk about. They all have the same measuring stick as the real number line, and the radian has that same exact measuring stick associated with it. Degree measure does not. Revolutions does not. You can easily convert it to radians and really kind of be speaking the language of having the same measuring stick associated with everyone involved. So, again, the radians are kind of the best measuring stick. You got a 0 right here. What is 0? What is 0 times omega, whatever the omega happens to be? 0 times omega is 0. Cosine of 0 is 1. Bam, E pi r squared is the maximum value. With it set at t equals 0, you get a maximum value. Over here, they're saying you get a minimum value. What does that mean? Well, it's everything we've done, only initially this thing is lined up so that initially the ring is sideways in relation to the E field. So the A vector goes that way, the E field goes this way. Initially, there's a 90-degree angle between them. The dot product of the two is 0, and that accounts for the minimum value. A minimum value that you also attain here, but you got to spin to 90 degrees, to pi over 2. You got to spin to 90 degrees, and that will do it. See what else I could say there on that. Yeah, that'd be about right. I mean, there's a lot to be said here. Let me not say too much on it, but let's. I think that's enough to say. Here's the big thing. You take that last thing that we wrote as an answer. e pi r squared, I want at t equals 0, I want this thing not to be 1, because that would give me the maximum value. I want it to give me the minimum value. We'll have the boundary condition that pi over 2, which is 90 degrees, add 90 degrees to the inside of the argument. You know, this guy's omega t for problem number 16. Over there, it's going to be omega t plus pi over 2. And they write it a whole bunch of different ways. I mean, and then you could, you also could have, I mean, since they didn't give too much specification other than the brief explanation that they gave, you could have had, and you can go minus pi over 2 from there. If you take it out of phase by, if you take the cosine function and either move it forward by 90 degrees or move it backward by 90 degrees, you're going to get at time t equals 0, you're going to get the answer of 0. At t equals 0, you're going to get the minimum size. So that works. And that in itself, I mean, you can beat this thing up pretty good, guys, I guess. And I'm not sure what the merit is of it all the time. But for the record, if you really want to play it that way, you got EA. If you add, and if you look at, there's the cosine function. If you add pi over 2, you make things happen earlier, and it ends up looking something like this. That's when you add pi over 2. You're making everything happen earlier, so what was happening here is going to happen over here. If you subtract pi over 2, you're going to make everything occur later. That's the sine function. This is negative the sine function. So again, this is, what you got here is sine of omega t, or something. Let's just call it theta for now. And the theta happens to be omega t. For this right here, if you make everything occur later, sine theta minus pi over t, where this guy is just the cosine of theta. Here, you're going to make everything occur, so it occurs later. So it's here, minus that. If you make it occur earlier, so let me, forgive me guys, let me write these down. I think when I erase them, it might be easier actually. I think there's enough to be said, and I think I could mix this up quite a bit if I'm not careful. Let me say what I'm saying, and let me kind of like emphasize it in short order here. We got this. Now, this right here, so this works. I mean, this certainly works. We said if you make everything occur, if you do a subtraction, you are making what was occurring. Earlier happen at that point. In other words, so if you're subtracting, this becomes, for the record, and I'll try to explain this in a second, guys. And on this side, so if you're kind of staggering this thing, you're asking what happened earlier, and you're getting this. What happens if you are asking, you find out what's happening at a later time? You're basically getting this, which is negative sine omega t, which is negative sine omega t is sine negative omega t. You're basically, there's a lot of ways to do that, guys. So when it's doing this, if you flip it like that, you could also say if you put the negatives, negative of negative gives you the positive value, negative of positive gives you the negative value. So there's a number of ways to do this. Or you have a negative sign right here, negative sign, positive omega, negative sign, positive omega t. There's a lot of ways to write this, guys. So we got to, we can debate that a little bit. I mean, when we get to it, whenever we need to do so, I guess you could say. But for our purposes, you've got this. And for the other purposes, you got this. And and these are different phenomenon. We're just not being told in what sense the rotation is taking place, you guys. How you're looking at this. So, I mean, we kind of just see exactly if we gave a final answer on that. We didn't really say much beyond that, actually. There's a lot of ways you can do this, depending what the initial conditions are, depending how the rotation's taking place. I guess there's a lot of arguments that can be made here. They don't go into all that subtlety, understandably, to my knowledge, the people first talking about this, and it kind of makes sense. It can be more confusing than helpful. The boundary conditions, if they gave you more specifics on the boundary conditions, we could be a little more specific about this. But given what they've told us, any one of these four work. In fact, this right here and that right there are the same thing. And if you were to put a negative sign here and a positive omega t here, that's the same as this, is the same as that. This right here is the same as that. So there's a lot of ways that could play out in its own right. What I had said, and maybe hopefully it's a little bit easier now to look at. I mean, we can look at, from those two problems, let's talk about what we were saying, what I was trying to say earlier, and I think it kind of got a little mixed up. So, there's a lot happening here, guys. I mean, you could say that where to start, where to finish on this thing, I guess. That's the cosine function. That's y equals cosine theta or cosine omega t, whatever. If you move this thing over pi over 2 units, to move it over pi over 2 units, you want everything that was going on earlier to be occurring at a later time. So to essentially talk about that, you're saying, okay, well, at this particular point, I want, at 0, I want to see happening what was happening at negative pi over 2. Well, why don't you take 0 minus pi over 2? Why don't you take theta minus pi over 2, and that moves it, the minus pi over 2 moves graph to right. When that gets done, that thing right there is also simply the sine function that we're used to looking at. They're identical. If you were to move it, so what was that? If you were to move it now, again, I'm going to maybe run out of room here, guys. If you were to move this guy backwards, have everything occur earlier, then you're going cosine theta plus pi over 2. And that moves graph to the left. And that is simply, it's not this. It goes here, move it to the left. It's basically doing this. Well, that's the sine function, kind of, it's a lot of things. This is y equals -1 times the sine function. Yeah, you could say that. It's also, and again, now we've essentially run out of room. That's also the same as, let me write it over here, maybe that makes it a little easier. That's the sine of negative theta. If you take whatever was in the domain initially and you take the negative of all the domain that's here and subsequent to all this, if you take the negative of all that, you're actually talking about values that would have been attained here to the left. So all this will be over here. And if you take the negative of the negatives, everything that was going on in the positive is essentially going to be going on over here. So that's going to be over here, and that's going to be over there. It flips this way. Well, flipping it about the y-axis or flipping it about the x-axis results in the exact same thing. And that's where you're getting that. And that's why I've kind of delivered the speech over there regarding all that. So you have this, and here's your initial look at the whole thing. And then we got all this, I mean, you've already had exposure to this at some point, and so on and so forth. So you've got okay. So that's 16 and 17, guys, at least with the conditions that they've given us. A lot can be argued. There's a lot of perspectives you can take, a lot of views that could be given to such matters, arguably. So it's good. I mean, like, this is fine to visualize this stuff. There's a lot of visualizations. I can be looking down on something and it can be rotating relative to my reference frame counterclockwise. Correct. I could go underneath it, and in space, who's to say what's underneath or above or whatever, but I could looking down, it's going counterclockwise, and yet if I go underneath it, it's going clockwise. So there's subtleties to the argument here, I guess you could say, when we do this. Again, this is really what's important, the visualization of what we're doing right here, guys. 16 and 17 we just did. Let's go to 29. 29, they've got a figure there, 25.29, shows a very long tube of inner radius A and outer radius B that has a uniform volume charge density of rho. Find an expression for the electric field between the walls of the tube, that is, for small r between A and B, not inclusive. A is less than R is less than B. Find an expression for it based on what we've said. Okay, so if we're looking at this, Okay, I mean, I guess the drawing would say more than the actual words sometimes. Obviously, when you're looking at the drawing in the book, frequently you're not going to even draw it. You're just going to say, well, I already have a reference for this in the book, and we'll kind of take it from there. Okay, so let me just make sure. So, I mean, really what's going to help us on this quite a bit is going to be, see here, there's Gauss's law that relates the electric flux through a closed surface to the charge enclosed by that surface. And that plays a big role. I mean, so what we're saying here is, and we'll say a lot more, I mean, you know, we look at Gauss's law, and the flux electric is equal to the summation, well, not summation, it's kind of like a summation, but not, it's an integral. The flux electric is the integral over a closed surface of everything of the form E vector dot dA vector as they have been defined, and that will give you the Q, the total amount, the net amount of charge enclosed over epsilon naught, a constant for our purposes. So that's, yeah, absolutely true. The way it's looking, for our purposes, I think it's a good idea if we draw this at some level. It's not going to be a great drawing by any means, guys, but let's get a look at it and see what they're trying to say here. There's an inner and outer radius, and they're saying generally what would happen for any radius r that you're talking about. So we could we kind of see what I want to say here. Draw big enough, guys, that we can kind of see what we're doing here. They're saying, why don't you generally tell me what's going on here for any radius r right there. Always apprehensive about this. It's hard to see this, guys, at some level. Here's r. Here's a. And here's B. So there's that, and this is B. Let me try to, the way they drew this is, it's hard to label who's what sometimes. There's not a lot of room, guys. Perhaps I could have made this a little bit bigger. But let's see what we can say here. It's solid right here, guys. Pretend it's completely solid. I'm just trying to preserve the arrows. And this is, like I said, this is B right here. And we got something looking like that. So, okay, here's your perspective. They're asking for some R bigger than A strictly and smaller than B strictly, and give me some kind of idea of what we're looking at for an E field. Now they're saying here, again, it says here, shows a very long tube of inner radius A this figure we drew and that they gave to us shows a very long tube of inner radius A and outer radius B that has uniform volume charge density rho. Find an expression for the electric field between the walls of the tube, that is, where R is between A and B, and R is not equal to A and R is not equal to B. So what can you say about it? Well, they're telling us uniform charge density. So rho is, let me see what kind of, play this whole bunch of ways. The Q in, well, the Q in total, and it's uniformly distributed. I think it says uniform charge density rho. So it's well behaved in the sense that the charge density is equally dispersed throughout. Rho equals over the volume, right? True. That's the charge inside. Well, what's the volume? Well, the volume is a pretty fascinating situation. The volume has a cylindrical hole in it. It is a cylinder itself missing a cylindrical part of it. The big one is B, so it'd be pi, regardless of the length here, I guess you could say, it would be pi B squared times some kind of length under consideration. So what you're talking about area times length will give me the volume of the cylinder. Well, it's a very long tube. How long is it? Well, you can almost pretend it's infinitely long, but I can't really do the math with it if I literally say infinitely long. How about I just say L, the length, is really, really big. Pi r squared times L will work. That's all of this thing, not counting. That's all of this thing, including the cylindrical hole that is in it. It includes that cylindrical absence. If there was no absence whatsoever, it would be, if there was not this cylindrical absence right here, if it was not here, all of this would be red, all of that would be red, and it'd be pi b squared L. The problem is that's not the case. You are missing this much. Great. Subtract then. Okay? So, it's fine. It's the same thing I had earlier. I just, we said a little bit more, I guess you could say, regarding this whole thing. What's Q equal to? Q would be equal to the Q or Q inside, right? The Q inside is Q, and that would be equal to rho times the volume. And the volume consists of a big volume minus a small volume that's not really present. So you're getting the cylindrical volume that has the absence of a cylindrical entity that was there to begin with. It's been removed, so this is that volume with this much having been removed. Yes, certainly true. We know now the E field, they don't really say positive or negative, so we just make the assumption it's flying out there. The E field is perpendicular to the cylinder or any Gaussian surface that you draw everywhere. So it's perpendicular to any one of those that you draw everywhere. So it's perpendicular to that. So what are we talking about? Well, we're talking about if you're going to deal with this, Gauss's law for electric fields, what can we say? Well, we can say a whole lot. we can essentially say that this Q, which is equal to this, is just Q, then just put Q over epsilon naught. I mean, after you got that, put this over epsilon naught, right? Sure. It means Q in. I didn't write Q in, but it's implied. I mean, Q in, Q that's... Now, what is contained? What is contained there? Well, that's an interesting matter in its own right, because, you know, how much is actually contained, and we can kind of look at where it's going to go. So this would be... This would be the big picture, I guess. This would be the total amount of Q. This would be the total amount of Q that's contained divided by epsilon naught. Right. Right. But I want to know what happens not from here all the way to there. Though that's not a bad thing to look at. I don't want to just go from the edge A big all the way to the edge B big. And that's what I did right there. And that's, by the way, guys, if you get rid of this, this is the total charge that is present, right? And get rid of this right here. That's the total charge that's present. Sure. I tell you what, the A is the low end. Why don't you make it so that there's for the R? Well, it's not going to be as much. It's not going to be as much. And I'll say that's the Q in. The Q in would be all this at a radius R if you went and did this for this guy right here. Well, that's not as big as all the way around here. And I did the all the way around here first. This is not going to have as much charge. Why is it not going to have as much charge? Because it's not as much volume. It's not as much volume. And all that equals EA, which is the E field times the area. Well, what's the area of the outside of the cylinder, not counting the edges? What about the area outside of the cylinder? What's going on? I mean, there's a lot going on that way in its own right, but it's very long, so I'm saying, okay, I just want to see one part of it where there's a lot of cancellation going on, but not over here. So it's 2 pi r to go all the way around times L will give you the surface area of this blue thing taken all the way down the line. Taken all the way down the line. So what is it? E 2 pi r yeah. And that's where, certainly that's where this is, it's the same thing here, guys. You see that there's flux one way, flux the other way. But that's not, the net flux is going to be coming out, whereas in all other instances, it's what's within and then coming out. And on the other side of that, the way they got it set up, they're not worried about the edges, is I guess what we're trying to say on that one, guys. the way it's set up. I mean, there's an E field that way. We're saying there's probably another E field coming in that way and coming in the other way, but not around the edge as far as what's associated with this whole process. So let's see what we can say. I mean, the setup is basically that. Okay, guys, so what do you got? Why don't you take and solve for E? E becomes, there's an L here too, right? There's an L here. Let's pull that out. Somehow at the edges, it's not going to matter with the length of this thing. There's enough going on that I just want to see what's happening within a particular area, and it's not going to change anything. So the outside's not going to be an issue for us, but everything else is of significance for us. So let's have a look here, guys, what we're doing. Divide by 2 pi r L on each side. So you got rho times pi r squared L minus pi a squared L. I mean, there's a lot I can do here, guys. There's a pi, there's an L. Might as well just kill all the birds with one stone, I guess you could say. There is a pi, there is an L. Leave these guys here, you can't do much. But there's a pi and there's an L right here. That's identical to that. That's epsilon naught right here. That stays. Okay, let it be. Divide by 2 pi r L. So that's pretty significant. What happens is what we're looking at. I mean, you've got pi goes into pi one time. You got L goes into L one time. You got 2 epsilon naught rho all this. Okay, so we got rho of this let's see what we got here. Right, and then that's just 2 epsilon naught. Got a feeling I might have done some other stuff with it, but let's just see. Not really. So what we have here, guys, is this stuff points outward. The E field points out in a radial direction. Okay, yeah, right. The R was still there. I'm sorry, guys. Yeah, there was still. We could have sort of gotten rid of the R, but it would have been kind of a mess. 2R epsilon naught. That is, and again, the assumption is the flux in and the flux out, they cancel out for the edges, but not here. And they're doing this. And for that's it. Those are ones up there. We know that. I'm just give myself a little bit of room. We're doing it. That's it. End of the story. For all this. Okay, guys, looks pretty good. Talk about different things that can happen here. They show us that in the book quite well, and we're looking pretty good. All right, that's 29. 30, problem number 30. Two very long, thin, charged rods lie in the same plane. One rod is positively charged with charge per unit length of plus lambda, and the other is negatively charged with charge per unit length of negative lambda. Okay, same magnitude of charge, you could say. The perpendicular distance between the rods is capital R. Use the coordinate system shown in the figure. Sketch the electric field as a function of R, as a function of small r, from negative R to positive 2R. Okay, as they got this thing set up. Okay, so let's take a look at that. All right, I mean, number of ways we could go here. Let me let's do some semblance of a drawing on this, and at least give ourselves get the bearings straight on this stuff, guys, when we're doing this. They're talking about one of the rods like that. And they're parallel. The other rod, like this. Assume they're parallel, I guess, right? This guy's got negative lambda charge density. This one's got positive lambda. Positive lambda charge density. The distance between them, again, you got to be careful here how they're saying that. This is kind of right like that. There's a number of the drawing that they have in the book is fine. The assumptions have to be fine as well, though, that we're making, and that's kind of on us to kind of know what's going on here, guys. That distance. Right, that distance is R. Perpendicular distance between them. So we got that. They've got the coordinates. I mean, the way this thing is written, I mean, it's just, I'm kind of debating the coordinate system itself. If you were to go here, there's no good way to draw this, I don't think, but okay. Let's just say this is 0. This is whatever it is. And this is R, the distance between them. This is not a good drawing, guys, but it's just debatable how you want to actually draw some of this stuff when you're drawing it, I guess you could say. But let's write it like that. That's 0. Now they're saying if this is your frame of reference, here's your 0, here's all the data that you got. What do you want to say about it? And they want, sketch the electric field as a function of R from negative R, E sub R. The electric field is a function of R. It's a function of R from negative R to 2R, big R's here, right? For this or from, okay, so we're asking for that. So let's see what we want to do. Sketch electric field is a function of R from this. I mean, there's a lot we could say. Let's actually do enough mathematics so we can actually visualize what the heck's going on with this whole thing. They're saying essentially, guys, that's all the stuff we've been saying in the past. Say this. Equals Qn over epsilon naught. They're thin, they're very thin, very long wires, so we're really not considering a lot here, guys. I mean, we're considering, trying to just figure out some ways I can say this. Okay, so you can look at it like this, and then you could say, okay, well, each one of these is a very, very, very long and thin cylinder. Yeah, I guess you could say that. It's very, very thin, though. They're very, very thin, very long. So I'll tell you what. What do you say to two very long, thin charged rods. They're still rods, guys. They're still rods. They still are cylinders, I guess you could say. What do you say? You draw a Gaussian surface, and you say that for this to work out, we've already said this significance, but let's work with this. Is it okay to say for each one of these, or for any one of these in general, you can say, let's just not get specific just yet. Let's just say E times 2 pi r L. That's the Gaussian surface. In other words, you go a distance r from here, and 2 pi r is all the way around, multiply by L, and you've got a Gaussian surface. All right, true. So if that's the case, and they've talked about how the stuff at the edge is not going to be an issue. We're saying that the stuff's so long, we're dealing with the stuff coming out radially outward. So what we can say is 2 pi r times L is the volume. Forgive me. No, it's the area. 2 pi r times L is the area of the Gaussian surface. The area of the Gaussian surface. And that's equal to the charge over a length L. The charge over a length L, which is lambda times L, divided by epsilon naught. This is charge divided by epsilon naught. Charge divided by epsilon naught. Charge per unit length times length will give you the charge over epsilon naught. Lambda times L over epsilon naught is Qn over epsilon naught. This right here is E 2 pi r L for the Gaussian surface under consideration. If that's the case, It's a lot to say. I mean, if that's the case, we've got lambda L. So the E field's going outward in all instances, guys, and there's a number of ways you can say that. Just want to see something really quickly here. So the electric field always points outward, you guys. The angle phi between epsilon naught and dA is 90 degrees for both the surfaces on the side. Therefore, the dot products are 0. And integrals are 0 for surfaces L. See exactly where they went on this. It's not very clearly shown here. But that's essentially what we were saying earlier, guys. So there's a 90-degree angle between what goes on the edges. The E field and the A vector and E field are going to be at 90 degrees from one another. So when you do the dot product, they are 0. So we've got lambda epsilon. So cancel lambda L over epsilon naught and 2 pi RL. The L's cancel. All right, I've not said anything really definitive here, guys. I mean, incredibly definitive, but this is the structure of what we're looking at in the circumstances. Let's just get the signs right when we're doing this whole thing. So what's going on? Well, I mean, there's a lot going on. So you can basically say, for this right here, for the positive L, for the positive lambda, true. For the negative L, for the positive lambda, we just said what we said. For the negative lambda, how is that playing out? Well, I mean, we said what you got here, guys. For this guy, for the negative lambda, this distance from here to somewhere. I mean, I almost don't want to go from here to here. That's a length r. True. For where this thing starts, we're going to do a Gaussian surface. If you're going to do it here for the same point, well, there's a lot going on here, but this length is r, this length is capital R, small r minus capital R is this for this guy right here. And the other guy is the straight out R. So this guy's R, and this guy's R minus R. Right there. So when you're going to do the same kind of Gaussian surface, but you're not going to use small r, you're going to use small r minus big R. And it's going to be going inward. So that's kind of interest. What's going on here, guys? Let's put this down and maybe explain it a little bit while we're actually working it. Same kind of mathematics is going on. but the radius is 2 pi r epsilon naught. 2 pi times the quantity r minus r, epsilon naught, and a whole lot of stuff here. The L cancels. There's an L in there and all that other stuff. Now, what is going on here? What is going on? This one is associated with an E field going out. This one is associated with an E field coming in. So, if it's going, is that always the case? That's the point. I mean, if you go here, it's going out. If you go here, it's going in. Let's try to actually see what would be for a particular place under consideration here, guys. We'll have to say what we're trying to say here, guys. I guess we have to be exceedingly careful when we're doing it. It's this and if you switch it up, there's a negative L, change the sign here and then change the sign here and you're fine. Let's see if this is okay. Yeah, I mean, you're adding these two and you're also adding... All right, so that's not very obvious, I mean, at first glance. These are equal. These two are equal. And that's where they're getting to here. For negative lambda. Okay, I mean, at first glance, it doesn't look like it's going to go that way, but that's the way it goes. What's happening here? Well, this explains it. This explains it fine. If you are here and you're going to there, the red one, here going to there, you got an E field going out this way. You got an E field going out this way. If you're here, doing all that stuff, you got an E field going in like that. So there's this is like the second guy, the negative lambda. The negative lambda guy, we'll call him E sub 2, and this is E sub 1, the positive guy there. Look, we've drew the Gaussian surfaces. This red thing is a radius that rotates. You rotate that radius all the way around here, and you draw a Gaussian surface, which is a cylinder. The edges are at 90 degrees that way and that way, whereas the E field is at 90 degrees to the curved part of the surface. E field this way, area that way for the edges. The dot product of two vectors at 90 degree angle to each other is 0. And that's why we only care about the stuff going this way. Well, the positive lambda gives you an E field going out. True. If you draw the cylinder here. If you draw this cylinder at that point, it's R minus R, goes up, but that's coming in. Okay, sure. Well, let's add those two. Yeah, okay. Add this, which is the E sub 1, I guess. Let's just call them, that's the E sub 2. I did a little differently in my notes, and this is for the other one to call that the E sub 1. Add the two. Add the two, yeah, that's where the subtraction comes in. If you rewrite it like this and add them, there's really that subtraction as well, but you just can't see it as well. But it has all these other things that look so much alike, and it makes it easier to do it. Well, okay. That's it. It works there. Is that always the case? Well, we know outside of here that is the case. We know outside of here that is the case. They were asking for negative r to 2r. So let me see here. Right. So let's look at all the scenarios. This goes from where you want to go? Go from 0. Go red here. From 0 to r. 0 to small r. And then the other one goes from 0 to small r, and this one goes, so this goes a distance from 0 to small r. A distance from 0 to small r is small r. And this goes a distance from this small r minus the big R here. So small r minus big R gives you small r minus big R is this. And we said all the monkey business that goes on. And we got something like this happening here. Now, I don't know if the magnitudes, relatively speaking, are really looking like this, but we do know there is a tug of war, and you can add them. You can add the negative and add the positive, and you're okay. Well, this is the same as that, as I just said, so we're okay. Why don't you come in here? You come in here, you're going 0 to some r, true, 0 to some small r here, and that's whatever it's going to be. And then this one right here is going to be so from here to here is small r. From here to here is going to be big R minus small r. Oh, wait a minute. Big R, actually, no, that's true. That's absolutely true. If this is small r and this is big R minus small r, get an answer. It'll around here, it'll draw it inward. Here, it'll draw it outward. Yeah, now both vectors are going together, but still, the addition says it. Why is that? Because that's small. In between the two wires, small r is smaller than big R. Small minus big is a negative. What's a negative divided by negative? Positive. It'll give you the positive. It'll add that way. It'll add that way. And the mathematics here can get you here. So still good. All right, looking good. They're not. There's some other items, I guess, under concern here when we're doing this. But let's see what the heck we could say here. These things get. There's gonna be limits on this where it's not gonna look too good, you guys. When we do some limitations, we'll cross that bridge at another time. Here is capital R. Here is capital negative R, right here. Well, capital negative R is still R. It's still R. Yeah, I know it's negative R over this way, but it's still radius R. And what would that be? Well, that would be put in R, a capital R for this guy, and it's going to work. Yes, but at what point? It goes this way, but over here it goes that way. So E would be going this way, over here. And anywhere from 0 to negative R, anywhere between there. This guy would have an E field. What would it be? So it'd be some R. It'd be like a negative R, I guess you could say. It would be for whatever R you got. R right here is a negative number. What would it be from here to here? Well, we said that would be a negative R minus a positive capital R is a negative number, is a big negative number. A negative minus a positive is even more negative. That would be drawing this guy this way, it would show. It'd be negative. True. Negative divided into something negative is positive. Yeah, it would be going in the positive direction. The other one would be going in the negative direction. And you got a negative R here. That would be telling you the negative direction here. And this can also be converted to that. No problem. You're adding these across the board, guys, and it's going to work. There is some kind of an issue if you're right on the actual, if you're right on the long thin tube here, or right on the long thin tube there, because you don't really know the width of the long thin tube, nor do you know its volume charge density. You know only its linear charge density. So kind of watch out. So look, yeah, we looked at, this is a touchy matter right here. If this was a cylinder, and that's a cylinder, they are cylinders, and you knew the volume charge density, there's games you can play there. There's perhaps something can be said there regarding what's happening with the volume. If you had volume charge density, there's stuff you could say. There's stuff you could say with volume charge density. Being infinitely thin wire here and being an infinitely thin wire here, there's an issue with this Gaussian area, I guess you could say, as to where you're going to do this. You know, how this actually, if there's no radius associated with it, it's really no area. And so what are you talking about as far as an E field is concerned? There's some matters of concern here where this, it tends to blow up at these critical points right on the actual wires. But to the left of both wires or between both wires, to the left of both wires or between both wires or to the right of both wires, all of this mathematics holds. So let's write it down, let's talk about it, and then let's draw it a little bit, and let's see what we can say. All right, guys, let me just check here that I don't have... Okay, guys, my mic had gone. Mic had gone at some point, guys, but this is where we are. So you're looking at this. This mathematics is fine. Hopefully, we haven't lost too much of the audio on this, guys. But let me, in case it has left at some point or another here, guys, we can say that, again, you're doing a Gaussian surface, you're doing it twice in two different scenarios, and you're finding out what the E field can be in two different scenarios. The E1 scenario is associated with the guy in blue, and the E2 scenario is associated with the one in red, and we've playing all this here to find out what's happening. So to actually do this, I mean, let me just, all the mathematics holds, guys. To make a long story short, when we actually got this thing to work, the setup works no matter where you're located. Anywhere to the left of the wires, the mathematics works. Anything between the wires, the mathematics works. Anything to the right of the wires, the mathematics works. To the left of the wires and everything else. So let's see this, guys. We said the mathematics that I showed up there should be fine. We said at the end of the day, right, and that's, and that's associated that way as far as a vector quantity is concerned. In both places there, assuming you stay in the plane. If you get off the, if you stay in the plane of these two wires, if you get off the plane of these two wires, it's a different dynamic. If you get off the plane of these two wires, you've got a particular distance here coming out this way. You get the red guy with a particular distance coming out this way, and the blue guy with another particular distance there, and they don't add up like one's R and the other one's capital R minus R, or R minus R. Here they work like this, always. Capital R is this distance, capital R is this distance, and small r minus capital R. So capital R is this distance, and small r minus capital R is the distance associated with the blue. So the blue is always associated with the small r distance from the red minus capital R, and the small r distance is just the distance from the red. That works right here where I showed you there was going to be a tug of war with the red one the red one doing a pull that way and the blue one doing a push this way. But even if you go here, the mathematics right here holds. It really was, as we said, and like I said, guys, the mic went out on me. The mathematics had it at R minus R, the negative L. Yeah, but if you switch them just for the sake of convenience, small r minus big R, that's the way I was doing the problem initially. Small r minus big R, and everything else here divided into negative lambda. Yeah, but if you switch this from small r minus big R to big R minus small r, you've reversed the sign. Okay, then reverse the sign one more time. And you get this. And this scenario, why are they plus? Because this is really a minus. So you got the positive, if you allow me to say it, a positive E field, a negative E field. It's this E field magnitude minus the magnitude of this E field minus the magnitude of that E field, or simply just add the two E fields. One's positive, so to speak, to the right, one's negative, so to speak, and that negative was already here because we had a positive number down here and we had negative lambda. If you switch, when you had small r minus big R, switch it around, big R minus small r, then you got to switch around the negative here, and you're still getting the same mathematics. Again, when the mic went, I don't know when the mic went, guys. I'll be looking at the film, I guess. But that same dynamic holds here. And the same dynamic holds here as well. We just can't deal with it right on this infinitely long wire that's infinitely thin. Nor can we do it right there. We don't know what kind of an E field we're talking about. Because if I bring this guy to 0, it's undefined. If I bring this guy to 0 somehow, that's also undefined. So there's 2 places it gets undefined. When the small r is equal to capital R minus small r is equal to capital R minus capital R is 0. Wow, it goes to infinity. It doesn't matter what this one is at that point. You put a capital R right here. That's fine, whatever. Or when this guy is 0, and then this becomes capital R minus 0. Well, that's fine, but this 0 blows up too. So it blows up in 2 places right here. Everywhere else, however, whether you're talking about here, or whether you're talking about there, or whether you're talking about there, this mathematics is valid. Okay, that's what I was trying to say before the mic kind of went on me. So as we look at it, guys, let me check my mic all the time now, I guess. You got this. It was written a lot of ways here. I didn't really put the vector notation there, and I probably should have. Well, I'm putting it in now. So you got lambda two pi epsilon naught 1 over r plus So what's going on? We said what we said. It goes in the r direction. You can kind of, it's debatable with this radius vector, guys, because there's a lot of radii that you can have here. This is true for the radii, provided you only stay in this plane. It's still an infinite number of radii, but you cannot go into 3-dimensional space and generally be getting the answers to be consistent with this if you're going into 3-dimensional space. So watch out for that. It's only within the plane, so I can almost take that off there. It's okay if it's in the r vector direction, but the unit r vector direction only while you're in the plane. Only while you're in the plane. Okay? Well, what are they saying here? Well, we basically said, as far as the size of the E field is concerned, that's a great point. What is going on here? Well, if you put in negative values, see exactly what we can say here, guys, on this one. Let's talk a little bit. Let's say, okay, we're believing the math. Let's make small r negative r. Let's make small r negative capital R. Capital R minus negative capital R is 2 capital R. Okay, gives you something. This is negative r right here. And so how's that going to play out? Well, there's a lot you could say here. This is going to be negative 2, which is negative a half times r. And this is, negative a half times, negative 2 capital R means bring the negative 2 out to here and go negative a half times lambda over 2 pi epsilon naught times r. And if you got the negative r here, you've got, for that r, for the other r, you got this. Trying to see exactly how I'd want to say this, guys. If you've got a negative r here, you got an answer. You got negative 1 times lambda over all this business with an r in here. Negative 1 times all of this with that on there. So let me kind of let's kind of hit the outskirts of this thing, I guess you could say. It's a lot you could do here. Let's draw the positive guy, positive wire doing this. Let's draw the negative wire doing this. This is R. Let's hit the outskirts at least. Negative R, negative capital R right here. Capital R minus negative capital R is negative 2 capital R. Take the negative 2 out of there, it's negative a half times all this with a capital R present. Negative a half times all that. Here, put a negative R, it's negative 1 times all that with a capital R present. That's negative 3 halves lambda 2 pi epsilon naught R. That's going to be a negative answer. So the E field here, let's see what they're actually saying here with this. So I guess the way you want to kind of look at it, you'd say these are all negative. There's going to be negative values here, guys. And the way we basically drew it was, this is between 0 and R from here to here. And what's going on with that is going to be pretty positive. So we said if the more you go to either edge in between the two, it's going to tend to be really big. So let's go from the in-between first, guys. It might be maybe easier to look at. What I had said last time was if you were anywhere in here, there is an E field going out. With this guy, you got an E field going in that way. Well, going in that way is the same as going out that way. Going out that way and going in toward the same way, you're adding them. They become more and more. As you get closer to here, it starts getting huge. As you get closer to here, it starts getting huge. Because the Gaussian surface that you're talking about, at that point, you're talking about there's a 0 right here, and that's huge. That blows it up, even though it just leaves it at R right here. And when you go to R, that's a 0. Even though that doesn't blow up, this does. So on the edges, according to this, it's going to blow up. Everything else is going to blow up to something very, very big. So if you go close to here or close to there, close to this guy, big positive answer. Close to this guy, big positive. And it gets bigger and bigger. In the limit, goes toward infinity. If you go on this side, near this one right here, you're drawing something to negative values, like real negative values, big time. And this one it's a finite amount. This goes toward infinity right here. It goes toward negative infinity when you're doing that. The numbers, so it gets big and it goes toward negative infinity. The other one was pulling it toward it well, so in here, anywhere you're here, this guy's pulling it toward him like that. It's pulling toward true, and that's going to positive values. Here, pulling toward goes to negative values. And it's really, really big negative, really, really big absolute value negative values and small positive values here. So what happens is it's really negative, and the further out you go, it's going to go towards something positive. So they're talking about something like this. This one over here, it's the same dynamic. It's going to be, if you go here, it's going to shoot out toward a really, simple as that, it does that. This will shoot out toward a negative value. Why is it? Because it's thrown out this way. And the closer you get to this, you go more toward infinity. If you go further out, this will be, by virtue of the Gaussian surface, there's going to be, when you're doing the division, there's going to just be a bigger value, the negative, as we say here. That's a negative r, so it's going to be a negative value here. The other one's not going to be as negative. If you go all the way out to negative r, you guys, this is negative 1/2 times lambda over 2 pi epsilon r, and this is negative 1. So this is more negative. So it's going to get more and more negative as you go out to a certain point, but it's not going to, it's going to reach a terminal value there. In the meantime, anything, let's say, smaller than that, let's say you went to negative 1/2 r, let's say here. For negative 1/2 r, you got negative 2 lambda over r. And if you had negative 1/2 r here, negative 1/2 big R here, you get 3/2 r, which is going to be 2/3. Which is going to be 2/3 r. So 2/3 with the r there, and this is going to be negative 2. So let's see, let me just try that again, guys. 1/2 here. If we had r here, and the half, that would be capital R minus minus a negative capital R over 2. That's plus 3/2, that'd be 2/3. That'd be 2/3 of a particular quantity. Here, the negative 1/2 would be negative 2 times a particular quantity. It'd still be negative, but not, it'd be even more negative actually. So you're getting, the closer you're getting to lambda plus, when you do that, you're going to reach a certain point, and then down here it's going to go infinity. So down here you're going towards some kind of infinite magnitude. Down here toward, if you're close enough, far to the right, move from the far right over to the blue rod, which is negative lambda. The closer you get to the blue rod, the more of a negative answer that you're going to get. It goes to negative infinity. The closer you get to the blue rod, the closer that you get to the blue rod from the far right. From the far right, going leftward toward the blue rod, the closer you get to the blue rod without touching it, you're going toward negative infinity for the E field. From the far left, getting closer to going to the right to the red rod, the closer you get to it, the closer without touching, you will go toward a negative number as well. And we saw that also. Why is that true again? Because when you actually get, actually doing this, and you actually get to the distance of, the one here to get for this guy to go a distance capital R and this guy's 0. If this guy's capital R and this guy's You know what I mean? If this guy's capital R and this is also capital R minus capital R is 0, it blows up. You get close to it. As you go toward that. It blows up toward what? Well, it's going to blow up toward a negative. As you go to the negative, it's going to blow up to, let's see here. Let's exactly see what's going on. That's a negative, yeah. So it's going to pull it this way, positive value. Also, you get closer to this guy, it's going to go positive value also. So in the middle, between the two, as you get to the edges, it goes really, really huge. In the middle somewhere, it's going to be a minimum. And where that actually is going to play out, you guys. So you can. There's a whole lot you could say here regarding this. You could say where the max would be in that regard. So pretty interesting stuff. It doesn't. It's all of this plays the way we said it plays. I mean, it's as simple as that. You're getting close. If you're within these two places, as you go to the red, you are going to be going the way this thing is working. This thing's going to go toward an infinite value. You're close to the plus lambda. If you go close to this guy, it's also going to an infinite value. Somewhere in between, there's got to be the minimum where it's still going to have some kind of a value. It's going to be a positive value, but it's going to be something finite. Over here, you're approaching infinity. Here, you're approaching positive infinity. Here, you're approaching positive infinity. And here, it's going to be some kind of minimum there. Same thing here. Here, you're approaching, this negative guy is drawing it that way to negative directions. You're approaching negative infinity on this side of the lambda, of the negative lambda. Well, here's your negative infinity. We said you're going to positive infinity on each side of plus lambda and negative lambda. If you're between the two, the limit as you're going to negative lambda, staying within here, the limit is going to positive infinity. The limit here, as you're going to plus lambda, is also positive infinity. You got this. If you go on the other side of that, it is going to draw, negative lambda is going to draw you toward negative values, and it's going to be negative toward negative infinity. The bigger you go, it should be something looking like this. It should be, or whatever it's looking like, it should be something finite. Same thing over here. This is positive, but yeah, I know, but on this side of it, it's pushing that way. That's to negative values toward negative infinity. And that's where this guy is toward negative infinity right here. It's a hard one to kind of talk about, guys, to be honest with you. But it's there. It works. They talk about it, and that's kind of how it's looking. If you looked at this and you took the derivative with respect to, you could get max min on something like this. You're assuming there's probably some kind of minimum right here for a value. At no point, I mean, I guess you can say something of great interest here. If these guys are equal, the E field is going to be equal to 0. Well, if small r is capital R over 2, capital R minus capital R over 2 is capital R over 2. 1 over capital R over 2 is 2 over R. If this is capital R over 2, then this is 2 over R. No, see, it's still, something's coming up here, guys. So we're still getting some kind of value, though. We can look at it, and like I said, we could take the derivative of this thing with respect to R and see what would happen here. If you took, in terms of magnitude, dE d small r, how we're walking, and you actually did that, you'd get lambda over 2 pi epsilon naught. These are constants all over the place. Do the summation rule, and you're getting -1 over r squared plus And the derivative here would be, it'd be -1 over the quantity capital R minus R squared times -1 by the chain rule. So -1 times -1, -1 times -1 is 1, and it's R, and you're getting this. Pretty neat stuff. This, you know, it takes on some pretty fascinating values, guys. Even here, it takes on a slope that goes toward infinity in some regard, guys. If I put a 0 right here for small r, this thing goes toward -infinity. Oh, depending where, now it depends from where I'm actually doing this, but you're getting a magnitude of -infinity if you put for small r the number 0. If you put the number 0 here, capital R minus 0 is just capital R. That's not a problem. But 0 right here is a problem. This has magnitude of going toward infinity. If you put a capital R in here, that doesn't do anything, but here it goes toward 0. And once again, so we're seeing something happening here. This is at R, you know, this is R equals 0. This is R equals R, and yeah, you even here, the derivative, the slope goes toward infinity. What does that mean? The whole thing's going toward infinity is what it means. I mean, this thing's, it's kind of out of control at that point. It's kind of undefined at that point. Now, is there a way, you know, is there a place where it's 0? Is there a place where that thing, that's kind of what would be telling us right here. The interesting part here is that as the numbers, if the numbers are less than 0, well, you can kind of see here, it's kind of an interesting point in its own right, I guess you could say. If the numbers are less than 0, you are getting an answer, again, negative, you're getting a negative slope in both circumstances. Well, at least here with the R, as you're going to R equals 0. So in both instances, you guys, look at the slopes. It's a negative, you know, here's a slope right here, here's a slope right here, these are negative slopes. And that's indicative of what's going on right here. Here, this is a positive slope. Yeah, I mean, you throw a number in here, you throw capital R in here. Yeah, I know that's negative. Throw capital R in here as you're going toward R, no matter where you're going, whatever number you're getting, if R is really, really close to R from either side, this is a big positive number. And even here, the slope's big positive number if you're going towards, you know, for one of them, you got a big positive number here, and I'm sorry, a big negative number here, and a big negative number here, and if you're going toward the R, this is a positive slope. Here it's a negative slope, and you know what? Yeah, that makes sense. Wonder what this is right here. Why don't you set it equal to 0? Set it equal to 0. These two guys got to be equal to 0. If they're both equal to 0, we set that equal to 0. Yeah, there's a number of ways you could play this, I guess you could say, right? If you took a look at this, if you know, there's a lot of ways to look, I guess. Here's R minus R over R, regardless. Let me take the square. Let me multiply by R squared on each side. Let me divide by 1 on each side. How is that going to happen? If this is R over 2, if small r is capital R over 2, capital R minus capital R over 2 is R over 2. If this is R over 2 over R over 2 is 1. You square it, it's still 1. R over 2. This is from R equals 0 to R equals R. Right in the middle, you guys, you get the min. Yeah, what else? You could do a bunch of stuff here. You could also have one negative, one positive, I guess, depending how you want to do it, where they're going to be. I mean, where else are you going to get a 1, I guess, you could look at. But as you solve this, you could find out what's going on. I mean, you could look at it, you could set this thing up and say, okay, you got this, that's 1, square root of both sides. You know, you could do a whole bunch of stuff. You could say, R squared over capital R minus R squared equals 1. Square root R over R minus R is plus or minus 1. And, you could do a whole lot of scenarios there. You could go for the plus scenario. Capital R is R minus R. And play that. I mean, you could do it like that for the plus scenario. Just put the plus scenario here. Multiply by big R minus R. Big R is going to be to small r. R is equal to, okay, well, we already showed that. We already showed that one. On the minus scenario, you put a negative 1 right here. And so you got negative 1 right there, and you end up getting R equals negative R. Negative times negative is positive. That about right? Yeah, it's not gonna. I guess there's only one place it's gonna work, guys. It's starting to really look that way, isn't it? That's negative R. Negative of negative is going to be positive. 0 is going to be equal to negative R. Yeah, that's not really the reality of how it's depicted. But certainly right here, we see that it's going toward infinity here on the left-hand side, and it's a negative slope. And what's going on is this thing is dropping off as you approach, moving to the right. It's dropping off to negative infinity. And here, this is indicative of this slope in the limit going to the slope here goes to negative infinity, which means that there is a very big drop. If you were to look from the left going to the right, you're really dropping off fast. It's a negative slope, goes toward negative infinity as you move toward R equals small r equals 0 right here, or as you move toward small r equals 0 from this end. In both cases, when we're doing that, this one's going to positive infinity right here, you guys. And right here we got positive infinity. So the big scenario here is, guys, that as you are moving toward the left, or as you're moving toward the right, it's decreasing, so it's going toward negative infinity. Here, as you're moving from the left toward the right, it's decreasing also, but it's going to the minimum right here. As you go from the right to the left, it's increasing. So there's a lot there, guys. I mean, with this scenario. So it's looking like this. Again, I'll check the mic, guys. I'm sorry I'm saying so much here, but I know I lost the mic at some point, so forgive me. I wanted to say at least something about it. Again, the notes should be easier to look at in that regard. I mean, you're looking at this, and I think they're making the way they're actually saying that, the way you actually got the answer. At the minimum, it's 0. So what is that? What actually is that value? And it wasn't going to work here, but we did get the R over 2, and that seemed to say a lot. There's where the symmetry was. If R over 2 equals R, that was your minimum, at least between the two places. If this is R over 2, then it's 2 times all this business with a capital R. Capital R over 2, the 2 flips, and you got 2 times all that. If this is R over 2, this is also capital R. If this is capital R over 2, then this becomes capital R over 2. And it comes 2 times that as well. So it becomes, as an answer, 2 times lambda. 2 times lambda, 2 pi epsilon naught, capital R, plus 2 times lambda over 2 pi epsilon naught, capital R. If you put, that's the smallest value it's going to get, as far as, and it's going to be a positive answer. As we can see, it's going to be a positive answer, and it has it as a positive answer up here. Is there a particular place it'd be equal to 0? Sure don't look like it, does it? I mean, it says, as we had the whole thing set up here, we did this, we got that. Let me just look one more time, guys, in case there's something kind of wacky here. No, that's it. It's not going to work otherwise. It's going to work with capital R over 2, and capital R over 2, the 2 flips upward. It's 2 times all this business with a capital R right here. This with a capital R over 2 is capital R over 2 in the end. That flips, and you got 2 times all that. 2 and 2 is 4. You're going to get 4 lambda, 2 pi epsilon naught, 2 pi epsilon naught over R, which is, so 4 lambda over 2 pi epsilon naught, that's going to be 4, that's going to be 2 lambda over pi epsilon R. That's a positive answer. So it doesn't go to 0. So it does make sense that it's up higher. The smallest it's going to get, it's over here. On the other side, there's no other place it's going to do a minimum like that, guys. It does appear that it's going to be, if you go far enough, you're going to get a set answer. This will be an increasing function throughout the process, apparently. I mean, as far as like the E field will go there. I don't think there's a point where it's, this will always, so when you kind of look at this, we talk about what happens, where it's going, and we can kind of visualize it and say, well, okay, if I go, as I go to the left, it's going to be, whatever it's going to be there, guys. You look at it and you look at the values, they're going to make it a minimum. Well, there's a minimum there. As R becomes very, very negative, you can, it does tend to get to be a big value. Actually, not a big value, but here, as R becomes negative here, and R becomes negative there, as we get negative values, for a given R that's going on here, this is going to be a positive minus a number. It's going to be a negative, but it's going to have a smaller absolute value than that's going to have. The R squared is going to have a bigger absolute value. As you go beyond 0, let's say, for example, there should be some interesting things that go on, guys. Again, we have to look at this. That's way beyond the scope of the problem that they're asking us. But it was something I thought we needed to kind of look at. All right, that's 30. 33. 33 shows a very long, thick rod with radius r uniformly charged throughout. Find an expression for the electric field inside the rod, small r less than big R. use, you know, the equations that we know how to use. Check your solution at the surface for small r equals capital R, and see how that all is going to play out, you guys. So just to look at this, guys, I mean, it just looks like it makes a lot of sense at a lot of levels. I mean, if we were to say that, you know, it said that there's an issue when small r equals 0, and there's an issue when small r equals 0, or when small r equals capital R, it's going to blow up. And it blows up this way, downward, on one side, and blows up this way, upward, on the other side. Same thing here. Downward on this side goes toward, and don't take this as kind of set in stone as far as like the thing where the coordinates are. We're just saying there's very negative values up here, there's very positive values over there, and then just take a walk. Here, it goes toward negative. And, you know, the derivative of it would be indicative of that. If you're actually looking at where it's going, how would you actually graph this thing? What would it look like? What's it doing? Well, we know that as you get big values of R, I mean, there's just at this point, it'll tell you what it's happening right there. We could say that if you're looking at, okay, at small r being equal to 0, or at small r being equal to 0, there's a problem right here, but not here. At small r being equal to capital R, there's a problem here, but not there. In both cases, it's going toward infinity. On either side, as you approach it, it's going to go toward infinity. Now, how's that going to work? Well, if you're on the side of coming close to this thing, as you come close to it, this tends to pull this way, but it's far away. Close to it here, it tends to push out that way. So as you're getting close to it from the left, this thing wants to go to negative infinity. So get close to it, taking a walk from the left, bam, it wants to go toward negative values. Because this right here, as you get close to it, this way, it's pushing in that direction. That's negative. This guy's tending to draw it this way, but it's not enough. This is going to push this way. As you get close to this rod right here, the red one, from the left, moving toward it, you're going toward negative infinity. You got this. So you got, it's going downward. It's going down toward negative infinity as you're moving from left to right toward the r equals 0. If you're going from right to left to r equals 0, this guy is pushing that way, positive values. This again is pulling toward itself that way. It's only helping at that point, but this one doesn't really need any help at that point, to be honest with you, because at small values here, wow, it's a huge, so it's going to positive, large positive here. Same thing over here. As you go toward r equals capital R, going from the left, get closer, closer, closer. Wow. This thing is pulling it toward itself. Yeah, these are positive. To the right is positive. That's going to be toward positive infinity also. So positive infinity here, positive infinity there. Just look really quickly, guys, if I could. Right, and then on the other side of that, it goes there, toward positive infinity, right? And then as you go to the other one, yeah, it's pulling toward it, so that's positive too. So, right, and the other one right there, and at the other place is negative, and then from here going toward it, it's going to want to draw it toward negative values, and it goes negative over here. It's all there. Is there a 0 here? I guess I'd have to try to set that, to set this whole thing equal to 0 and see what I can do. Sure doesn't look like it. You know, you could set it, you know, to see what would happen. Is there a way you can do it in relation to those? Set it equal to 0. 1, that means basically this, means 1 over r minus r equals the opposite of the other one. They got to add up to 0, so they got to be opposites. If you got to add these two and have them be 0, so this guy's got to be equal to the opposite of what he is right there. You could go r over r minus r equals -1, multiply by capital R minus small r, -1 times capital R minus small r. We've been down this path. Here's 0. 0 equals -r. Yeah, that's kind of an interesting point. If the r, if 0 were equal to -r, kind of a meaningless thing. If 0 were equal to -r, if 0 were equal to -r, 0 equals to negative capital R would have to be equal to 0. What does that mean? Well, capital R equal to 0 is all these charges which are negative, all these charges which are positive, they come together, they cancel. When they cancel, there's no E field. Yeah, it works. It works. Again, you don't need that kind of detail on it, guys, but just getting a general look of where it's going is pretty important. If you can get to here, this is really the big one. Get to here and manipulate with this. Take derivatives if you want. You can see if things are concave upward or concave downward when you take second derivatives. You can take first derivatives like we've done and look at it. We can also visualize just looking at the function itself and how is this thing behaving given the function that we have here, given this function. How is it behaving? And also you can there's a lot of stuff you can do. You can just look at the actual diagram and it gets you a lot of places. Okay, there's a lot there, guys. Number 33. Well, again, they've said here, this shows a very long, thick rod with radius capital R, uniformly charged throughout. Find an expression for the electric field inside the rod, small r less than capital R. Use the equation that we know, and we probably even derive it. E vector equals 1 over 2 pi epsilon naught times lambda over r times r hat to check your solution to the surface at r equals r. Okay, it should be pretty straightforward, you guys. Let's take a look at it. Okay, a very long, thick rod. So we're talking about from a very far away coming to here. capital R. And they want to see it when R, you know, what's behavior going on? What is happening here, guys? When small r is less than capital R. And they're asking for the usual, you know, how this all plays. Okay, well, how are you going to play it, guys? They want to know find an expression for the electric field inside the rod, where R is less than R. Shows a very long, thick rod with radius R uniformly charged throughout. Uniform charge density throughout, you guys. Okay, guys, sorry about that. All right, we've been here, we've seen this, guys. We know the deal on that. Let's talk. You've got, you know, E dot dA, the integral E dot dA, which is E times 2 pi r, the circumference of the Gaussian surface with radius r, which is less than capital R. That circumference times L will tell you the area of the Gaussian surface that we're talking about. Where it's applicable for us, okay? Then we say that's the same as the uniform charge density, rho, for volume. Uniform charge density, rho, times V. Charge density per volume, charge density per unit volume times the volume over epsilon naught. Charge density per unit volume times the volume is Q. Q over epsilon naught is going to be E times A. 2 pi r L is where it comes out to. The other dot products don't enter into it because they're at 90, the two vectors are, the vectors under consideration at 90-degree angles with one another. So the edges don't count. But the radial phenomenon under consideration do count. Back up, no way. I'm not talking about a sphere here, guys. I'm talking about a cylinder. The cylinder has volume, pi r squared times L. Pi r squared times L times the charge, the volume, pi r squared times L times the charge per unit volume gives you Q. Divide by 2 pi RL on each side. All right, a lot goes on. The L's cancel. One of the R's cancels. pi cancels. Rho r over 2 epsilon naught. It's in the radial direction. The other ones don't count. They add up to 0. They're there. There's other areas there on the edges, but they're not going to count. It's as simple as that in that regard, you guys. So we're looking at it. Now we confirm consistency with the charge with lambda linear charge density. Now that's kind of the interesting point here. They're not really, find an expression for the electric field, use equator to check your solution at the surface. Yeah, I mean, I guess you could say a lot at the surface, I guess you could say. I say here, now we confirm consistency with the charge. Now we confirm consistency with line charge with lambda, linear charge density. So we can kind of, visualize what's going on that way, you guys. So let's see what we can say here. We have said, just recently, very recently, I kind of beat it up pretty good. We talked about the linear charge density. We got E here. How does this compare? 2 pi r L equal, okay, well, lambda times L will give you Q. And that's Q over epsilon naught again. Lambda times L will give you Q. Q over epsilon naught is what this is all about. 2 pi r L around and then across will give you the areas that were under consideration here. Divide by 2 pi r L on each side. The L's cancel, right? Sorry here, guys. It should have been an epsilon naught right there as well, right? 2 pi r L, divide by 2 pi r L on each side, and we got that. The lambdas go. The L's go rather, I'm sorry. 2 pi r epsilon naught. Yeah, it looks familiar. We were really talking about it very recently. So we've got that. Right. Yeah, we were just talking about that, right? I mean, so is there a connection here, guys? I'm making this claim, and well, there's a lot of claims being made, I guess. That's if it's linear charge density. There's a lot you can say. I mean, the way they go about it is, let's just follow their argument, I guess. Is this true? Is this working? I mean, can we see a connection here? Well, can we? I mean, that's a great question to say. So we got two things here. can basically say this to kind of get yourself out of the woods. Rho times V, volume charge density per, charge density per unit volume, that's rho. Charge density per unit volume times volume will give you Q. And that's the same as linear charge density per length times length will give you Q. So that's what that means. We're saying rho is pi r, rho is rho, pi r squared L is equal to V. This is lambda and this is L. And we're saying this is, again, there's the point of intersection, so to speak, right? If that's the case, lambda would equal rho pi r squared L. Lambda would equal rho pi r squared L divided by L. That's just pi r squared. True. Okay. Lambda equals this. Rho pi r squared. Rho pi r squared. They're asking to establish, say they're equal to this. Rho, lambda equals rho pi r squared. Makes sense. This becomes kind of like the lambda. If you multiply it by L and you multiply that lambda by L, lambda multiplied by L is Q. This thing multiplied by L is Q. Interesting connection. That's the lambda. This is 2 pi epsilon naught R. The pi's cancel. These R's cancel, leaving just one R. And you got rho, the pi's cancel, one of the R's cancels. Rho R over the pi's and the R, so you got rho R, 2 epsilon naught. Wait a minute, that's what it is right here. So they were looking for a connection there, I guess. Can you say there's a connection? Yeah. If you're gonna have rho pi r squared behave like a lambda, it's consistent. If you have it behave like a lambda, it's consistent with how it's done. Now the lambda, you're doing the stuff that goes on with the lambda, everything is outside of that very thin wire. Everything was outside that very thin wire. You saw us argue about that forever. Everything was outside of those wires, and what's going on if you go right onto the wire? Well, crazy things happen. We already talked about that too. Weird things happen. But here it's consistent. If you're going to call this, it behave like a lambda, yeah, I guess you could say that. It has the tendency of a lambda as long as you are, it's as long as you're right on it, you can kind of say you're, it's almost like the lambda, you're R away from the infinitely thin wire. From the very, very thin wire, you're R away. Whereas with this, you're right on the surface. And it comes out to the same thing. And I think that's which is what we wanted to confirm when R equals R. So, you could say, yeah, is it going to be true that way on the very edge of something like that when R was equal to R? Well, if you put this guy at R, Just trying to figure out why they're saying what they're saying here, guys. I have it written here, and for some reason I just don't want to, which is what we wanted to confirm when it's going to work if you plug in a capital R right here at the surface, and you plug in a capital R right here. With the lambda, if you put an L here and a 2 pi R times L, you would have the Q that we wanted. So let me just try to think here with the area. Yeah, there's a number of ways to look at this, you guys. I think what you're doing is you are 2 pi R times L. There's enough symmetry here, guys. I mean, we see what's going on. I mean, that's for sure. So we're looking pretty good here. And like I said, I have it written out for you guys. If you're going to plug in small r equals capital R, it works just fine. Okay. Let's go to 34, and then we'll match up the stuff that's going on here, guys. Perhaps I need to wear my mic here in the back pocket. Probably easier to check on it. So we'll see how it works out, because I think we have all enough data that you can see where I'm going with this stuff. And like I said, all of this is going to be scrolling at the end when we're doing this stuff. I just want to try to just confirm what the heck some other stuff they're trying to say here if you're doing that at the surface. Basically what they're saying here is if you did put a capital R right here, and I mean while the whole process was taking place, you're saying it's looking like that. If you put the capital R right here, could it work? And actually, in place of all that, have a capital R here, and then capital R here, and with this guy, capital R away. Yeah, if it's just a capital R here, that would work as well, guys. At the end of the day, you can make it so if you had the capital R there, guys, you'd have essentially, yeah, you got a lot going on. I mean, but you got essentially, you've got the rho is Q in over 2 pi, forgive me, yeah, right, 2 pi capital R times L, 2 pi R times L, not per that, forgive me, that would be pi R squared times L. That's rho. That's rho. You know, and you could say, okay, well, is that actually a true story? If you multiplied for R, let that be that, and this is 2 pi, and this is 2 epsilon naught. What you get, guys, for the E, the R's cancel. You got pi RL. You can bring it down here. It's 2 pi single R L epsilon naught. You know, for anything under consideration there, that's R. That's what it looks like. Over Q in. Well, wait a minute. What's Q in divided by L? That's lambda. And it becomes Q in divided by L is lambda 2 pi R epsilon naught. 2 pi R epsilon naught at R. I mean, guys, you can, again, you can figure this out any place you want. I mean, let's just kind of make it look like that. It's going to be this Qn over L is lambda. It's going to be 2 pi, just write it the same way I wrote it over here. It doesn't really matter, guys, but I mean, 2 pi epsilon naught capital R. Yeah, I can assure you, I guess at the far edge, at capital R away. Now remember, this thing associated with lambda is a very, very thin wire. So you're going off the wire by a radial amount. You're going in a radial distance away from the wire, capital R amount. Capital R amount, you're going away from a perpendicular distance from the wire. Here, you're on this thick cylinder that is, you're right on that cylinder R away. On the cylinder this is the E field on the cylinder. R hat going outward. Lambda over 2 pi epsilon naught capital R. That's the E field on the cylinder. Distance R away. Plug in capital R here, you get the same exact value of where it's there. Yeah, absolutely true. Absolutely true. And the amount of Q in actually, where you got it here, where you got the whole thing here set up, guys, how the whole thing would play, yeah, if you plug in the R, you get that. So there's a whole lot of math we can do. When you were doing this over here, we got what we got. Now this right here is Q in over pi r squared L. Even with the small r it works. That's what I'm trying to say. This rho is Q in over pi r squared L. True. That's how much is there. You're multiplying it by pi r squared. The area, let's see here, rho, no, you're not going to multiply by that. You're going to multiply it by, as far as the area is concerned, it's going to be 2 pi r times L. Okay. And that whole thing is over epsilon naught. And how you can actually, how you can do this. So you could say Q in, yeah, that's the density. If you multiply that, yeah, whatever the total amount is, and you're multiplying by pi r squared L again, if you allow me to say that. So it's rho times that, times, that's Q, divided by, that's that, and then you'd multiply that by pi. That'd be the Q you'd get. You'd multiply that by 2 pi RL. And that would be equal to, that's Q over that, over epsilon naught, is equal to E times, E times that. So what you're looking at, I mean, let me leave this, guys. There's more we can say on this, but it does work out. We've seen enough of this thing that I think we're okay. Let's try one more, and then we'll get back together and do this again. Here we go again. For this one, for number 34, a very long line of charge with linear charge density lambda is parallel to another very long line of charge with linear charge density negative 2 lambda. So there's a very long line of charge with a linear charge. There's a very long line of charge with linear charge density lambda. And it's parallel to another very long line of charge with linear charge density negative 2 lambda. Both lines are parallel to the y-axis and are the same distance r from the y-axis. Write where the first wire is to the left of the origin and the second wire is to the right. Use Gauss's law and the principle of superposition to find an expression for the magnitude of the electric field at the origin. They just got to find out what's going on at the origin, guys. It should be pretty straightforward. Let's say it again. It's saying a very long line of charge with linear charge density lambda is parallel to another very long line of charge with a linear charge density of negative 2 lambda. Both lines are parallel to the y-axis and are the same distance r from the y-axis. So they're on either side of the y-axis, you guys. We're assuming, I think, that they're, I guess you could say a lot of things here. But we could make a lot of assumptions. You could play a lot of games here, but let's assume they're on. I think the way to look at it is the assumption here that they want us to make is that they're in the same plane, similar to the problem we did earlier, where the first wire is to the left of the origin, the second wire is to the right. Use Gauss's law and the principle of superposition to find an expression for the magnitude of the electric field at the origin. Okay, so how it actually works at this point, guys. At least at the extreme point that we talked about, capital R, everything works pretty fine. A lot of looks we can give it. All right, there's assumptions here that I think we have to make. They're parallel to each other. Well, okay, they said they're parallel to each other, and I think they're parallel to each other and they're in the same plane. Well, if they are parallel to each other, they are going to be in the same plane, and they're going to be on either side. They're parallel to the y-axis and are the same distance r from the y-axis. I think we got to say a little more than that. We got to say that they're parallel to each other. And if they're parallel to each other, they're going to be in the same plane, true. And if they are both parallel to the y-axis, they're also, I think we have to make the assumption that the distance is r for one and r for the other, and r away from the y-axis and r away from the y-axis. It's a little different. You could conceivably have a situation where they're each r distance away. They're parallel to each other, but they can be very close to each other, much closer to each other than being r distance away from each other. So let's watch out. I think there's some assumptions you just have to make here that the problem itself is not going to tell you. And it's not really a fault. It's not really the fault of people writing the problems. You just got to make certain assumptions sometimes. I think that's what they want you to do. We will assume y-axis here, x-axis here, we've got this one, and we got this one. This one's got charge density, negative 2 lambda. This one's got charge density, lambda. We already are rightfully assuming that the E field at the origin The E field at the origin is going to be directed to the right, given this scenario. What do we got? Well, we've done this. Compared to that long song and dance that we did earlier, this is easy. We should be all right. If this is the origin, and this is, like I said, this is R away, and this is R away, and that's not obvious, because you could, conceivably, if you want to play devil's advocate, they could be parallel. Two parallel lines are in the same plane. And if they're both R distance away from the origin, if they're both R distance away from the y-axis, perpendicular distance, and they're parallel to each other, and they lie in the same plane, they could be high up somewhere, be R, they could be from here to here is R, they could be here, they could be right here, and the origin's over there. From here to here is R, and from here to here is R. That's sure not R, whatever. There's assumptions we make, and I think we can make it here. The basic look here is you call one of them one of them the other, and we'll figure out what's going on. They're both at this place right here. So basically, guys, you've got E, and here's your Gaussian surface as you go around the thing. E times 2 pi r L, E times that area is going to equal the total charge, which is lambda over L, divided by epsilon naught. Remember, where phi E was equal to Q in divided by epsilon naught. True. Yeah, lambda L. Will that be for this guy? What about for the other guy? It's the same thing. They're both the same distance apart. E 2 pi r L equals negative 2 lambda over epsilon naught. What's going on here? Well, you got this one. We'll say this guy with the lambda right here, we'll say he's E1. We'll say this guy's E2. This guy is pushing that way. This guy is pulling the same way that one is pushing. Together, they add up. I mean, this guy is pushing to the right, and this guy is pulling to the right. You add them together, you're fine. Well, if that's the case, I don't worry about the negative. I can go minus a minus, I can go whatever. I can do a lot of stuff. I can say this E right here, divide by 2 pi r L on each side. The L's cancel. You got 2 pi r epsilon naught. 2 pi r epsilon naught for that one. We'll call that E1. That's associated with the lambda. The E2 will be this guy. Call this E2, call this E1 just for the bookkeeping. Divide by 2 pi r L on each side, and you get negative 2 lambda over 2 pi r epsilon naught. Yeah, it's negative, huh? Yeah, because it's drawing it towards itself. Yeah, this draw toward itself, this guy, the negative 2 lambda association, drawing it toward itself is the same direction. This drawing toward itself is the same direction as what this one is pushing. So you can add the two. You can add the absolute values. Or go E1 minus E2. Because we're assuming they're fighting each other. This is pushing that way. The blue is pushing to the left. The blue is pushing to the left. The red is pushing to the right. Let's subtract. Yeah, no, but that was a negative. Minus a minus is plus. So it'd make it look real good. I mean, so you're saying, to make a long story short, you could argue this a bunch of ways, as I always say. That's the same as, right? That's the same as lambda over 2 pi r epsilon naught minus a negative 2 lambda. In the end, you can kind of go around that and not even talk like that. I mean, you could just say, look, I know they're helping each other out. I'm just going to get the absolute value of the whole situation. And minus a minus, minus a negative, to the right. To the right, you guys. Yeah, like I said, I wrote it different ways. I went a little more on an instinctual level when we did it the other way. But that, to the right. Let me write that. So it's always a little cognizant of where the stuff is visible and where it isn't. Watch the assumptions that got to get made, guys, right? I mean, watch out. All right, guys, there's more we got to do, and we'll do them next time we get together. Let me leave it at that. Like I said, on something, let's however more videos I end up doing, guys, I'm always gonna be checking my checking the mic here a lot more. But anyway, whatever we might have missed on the mic, it should be. I think I maybe over talked on some of the stuff on the more difficult problems. I think you got everything you need there. You're also gonna have it in the notes that scroll through this thing, so you should be okay. All right. All right. Thank you so much for your time, guys. Take care.